everyone. My name is Sandy. I'm a group F's homework is WFS and redshift. And so I need to explain the dark band. The dark band is that you see this is the line. It names dark band. The dark bands are produced by absorption of light by the element containing halo of gas surrounding the star, which is producing light. And the packet of light can interact with the atom only if it has just the right energy. And you will see its partially darkened line in the spectrum represents a single element. And astronomers were able to estimate the element making up the atom space of neighboring stars. And you will see this picture. It has line C, line D, line F. And line C and F lines are created by hydrogen in the sun's atmosphere. And the dark line, dark dim line in the yellow are the most prominent lines of the sodium. And as you see, yeah, and this is our homework picture too. And you will see the spectral line shoots toward the red. You can see its dark band shoots toward the red. And more startling was the finding that the more distant the object, the greater the shoot toward red. And this is Doppler effect. The wavelengths can seem to be changed if either one or both of them are moving. And when the distance is increasing, the frequency of the received waveform will be lower than the first waveform. So you see this picture, you can find all other stars are redshift. And this redshift is the advance for the theory that the universe is constantly experiencing, which will support the Big Bang theory. And my homework is finished. Thank you.
Alright. Now, please return to all the slides. Right. Exit. Yes. Okay. I stand here. A student, status. Do you have questions, comments?
My comment, I have few comments.
Please louder.
Oh, okay, I have few comments. Maybe next time try not to speak the same words on the slides. More interact with audience and some of the vocabulary, the pronunciation is wrong. But I guess that is not that big problem. That's all.
That's all? No scientific comments? Content. Regarding her content argument. Any? Maybe I can start first because you are so used to the scientific English stuff. Okay, I will start first. Can you go here? Here. Show all. Alright. So here are all your slides. Okay, let me ask you first. 4, number 4. Slide number 4. Can you show it? How do they know it's from hydrogen and sodium? Any idea? Your guess. Reasonable guess. What is your title? What is your reasonable guess? How do you know?
Hydrogen is because the sun's atmosphere, and I think it's the from a Big Bang, and you will see the hydrogen.
Okay, stop. Student A, Jackie. How do you know it's from hydrogen and sodium? The answer is super simple. How do you know that?
They are at the same place.
At the same place? No. Not at the same place. Kevin, how do they know it's from hydrogen and sodium? The basic question.
Some.
No.
No, I just asked you. The some has hydrogen and sodium. Because
I'm
they are
asking, why do they know this band
this band
come from hydrogen and sodium? How do they know that?
Each element has its specific band on a spectrum, and so it can match the edge on the spectrum.
Half answer. Yeah.
We can look at some spectrum. The lines C and F also in the hydrogen, and the middle line is also in the sodium. So
Right. So actually, what I'm asking is, it's actually quite simple. They know that because they do laboratory experiments using pure hydrogen and sodium. That's how they know that. So here I'm telling you is, you think chemistry is all wet chemistry. 所有的化学都是湿化学, but it's not. Actually, light is chemistry, especially for cosmos chemistry. We use light to study chemistry, and this will be repeated again and again for the first few weeks. You study chemistry by light. Okay, so that's very important. Okay. And then the next question is, Group A student, do you have question for her? I have a lot. I can send some for you. Do you have question? You should have. Okay, Ian.
let's go to the page 6.
Page 6.
I think when you talk about redshift, you can also explain what is redshift. And when we look at redshift, we know it's a wavelength strength. But when we talk about wavelength reduced, it is also redshift.
So that's a comment for her.
Yeah.
Okay. He's asking, but I have a follow-up question. Why is this one? Is this one redshift or this one redshift? How do you tell? Is it higher frequency redshift or lower frequency redshift?
Lower frequency.
Okay, then I'm asking, can you go here? Then how do you know it's expanding? Why this tells us that the universe is expanding? Why? Any idea in Chinese?
Chinese.
Yeah, yeah. If you find it flat. Why? Here you say redshift, next you say expanding. I don't see the connection.
Because redshift is lower frequency,
Right?
and so you can推断
Okay. You can say.
就是宇宙在扩张，
Sorry?
就是
It's redshift, then you say it's expanding. What's the logic here? There's a missing concept. Alright, group A. Any idea from you? Okay, Jackie. Hi, louder.
Redshift means star is go far from Earth to work more power and the extended.
Okay, you say redshift means the star is going away from us.
Yeah.
How do you know that?
Because the effect, the wavelength being the frequency being lower and the wavelength being higher.
Right.
Yeah.
Exactly, that's a missing concept. Okay. Redshift means lowered frequency. And lowered frequency means the object is moving away from us. And therefore that means they are leading. Everybody is leading us. Therefore it's extended. Okay? Okay, let's next Sammy. You have to stand here. Because we take video for soil. So you can say hello to him. He's still in Fujian.
Okay, hello everyone. I'm Yang. And I'm group B, so I'll explain the figure 2 to 10. And
Can you display? Okay, right.
And look at this picture, we can summarize it in a sentence. The farther a galaxy is, the faster it retreats. And today is Kevin Chan's birthday. And imagine that, for example, imagine that everyone participates in Kevin Chan's birthday party, and in the end, we left in the same time. But some of us walk at 4 kilometers per hour, and some cycle at 10 kilometers per hour, and some of us drive at 50 kilometers per hour, and some of us have helicopters at 500 kilometers per hour. So we can see this. We imagine that we all travel for an hour. We all travel for an hour at the straight line, but heading off in different directions. So we can plot like this. We can see the slope means time, and everyone has the same slope because we left the party house together. And we can see the farther two groups are from one another, the faster they must be moving, retreating. And the same thing happens in three-dimensional spaces. So if we turn time around and move the various galaxies backward at the rate they are observed, and we can find that everyone comes at the same time and at the same place. That's it.
That's all your slide?
Yes. I'm explaining this. I use just for example, the birthday party.
Okay. I have tons of questions. Okay. Anna. Is Anna here? Okay. Do you have a question for Yang? Sorry? Okay, I give you a minute. Okay, Zhi, do you have question, comment for him? You all did the same assignment. You are fully satisfied with this explanation.
Our homework is going to explain the Big Bang Theory too.
So can you explain a little bit story?
It is difficult to explain it in English.
Okay, I give you 2 minutes in Chinese now.
好，就是刚才那个举例是说每个人离开那个 party house， 每个离开光辉家嘛，然后这就像是大霹雳的那个点，然后我们同时从那个点，就是宇宙在扩张，所以我们同时从那个点像是在远离彼此，然后我们可以观测到一个星系，它们远离我们的速度，还有它们跟我们的距离，然后我们可以把每个星系的这些资料都把它统合在一起，然后会发现离我们越远的，它离我们越远的，它远离我们的速度会越快。那把它全部就是因为它是直线的在往一个地方扩张，它是直线的往你远离，所以如果你用反方向把它推回来，然后那个就是用它的速度跟时间去推回来，然后全部的点都会刚好集中在一个点。然后对，就是这个大爆炸这个图的意思。
I have a follow-up question. Next slide. Here you say the slope is time.
Yeah.
The time of what?
Time of the retreating.
Retreating.
Yeah,
We are talking about the party, okay?
Yeah, they leave. The time they leave.
Right. The time they start to leave the point, the house, right? Okay, good. Let's see. Okay. Do you have comments, questions? Oh, yeah.
Next slide. So, why the velocity is proportional to the distance? Why that distance?
Oh.
Yeah. Right.
You mean the slope like this?
Yes.
Oh. We can see distance. This is the farther the galaxy is, the faster it retreats, and just like some of us take a helicopters to home.
Sorry, what did you say?
Oh.
If you feel stuck, you can just say, I'm not sure.
I'm not sure.
All right. I would rather say it's an observational results. And then the astronomer, they try to find explanation for this. Okay. So that's first observational, and then we look for explanation. And actually, I don't think the textbooks explain the explanation. So I myself, I don't know, because I'm not studying this. Okay. Anna, do you have some comments, questions?
How is picture can explain the formation of the universe?
How does it explain the formation of the universe?
It can explain galaxies. They are retreating. They are retreating from each other, and the far the distance is, the faster it retreats, and it just can explain this. Just this.
There are also blue ships.
There are also what?
Also blue ships happen in the universe.
There are also blue ships in the universe.
Blue ship. Okay. Blue ship.
If you don't know, then you say I don't know.
Yeah, I don't know because I make this PowerPoint and I read a textbook, but they doesn't mention about blue ship in this part. Yeah.
Any common question for him? Okay.
The professor said, and
because this this threat is by the observation. So what the object may observe and what is the method that the distance of the galaxy and the velocity of the galaxy. How do they know?
How do they know
I
this
think
and that?
textbook has said.
How do I know the velocity and the distance? This is how 天文学家
No, that's in the textbook.
No.
That's actually the.
No, I didn't read this.
Okay, then you read too little.
Okay.
It's actually very critical.
Really?
So do you know how do they know the retreat velocity and distance? How? If you know, then you say, I know. Blah, blah, blah.
Can I explain it in Chinese?
Okay, you have 2 minutes.
其实我不太确定，但是对，就是我在做这个 PowerPoint 的时候，我读的那部分就是没有讲到这个，可能真的读太少啊。然后我猜我想应该是用那个光的波长之类的，就是因为高中之前有学过蓝移也有听过蓝移跟红移，然后大概就是那个概念。
You are talking about velocity or distance or both?
Both.
Half right. Does anybody know something about this? How do they know the axis? Hank?
The distance, I guess, they use the triangle parallax.
Right.
And
Part of it. Right.
And
Velocity?
velocity just is open.
Right. The Doppler effect, which means pressure. Alright? So this is partly by triangulation, 三角测量法, and this is for the bidirection that Sally just explained. So you should know how they get the photographs. Alright? Okay, yeah, thank you.
Thanks.
So today we will shortly talk about the Big Bang. And I'm not the expert of this, I just know the superficial part, I just know the textbook knowledge. But I try my best to explain. So, questions about the universe. I guess this is, you learned something about this during your high school education, maybe. And the question is, of course, how big is the universe and how old is the universe and was there a beginning? So these questions, some of these questions look very philosophical, 哲学的. You probably won't think it's a scientific questions. Are we able to answer such big questions? It's almost like is there a God? Something like that kind of questions. However, the Big Bang theory is actually a very solid scientific theory. So if you read the textbook will tell you from the perspective of scientists. They would say, if a perfect theory has 10 points, 10 分, then the Big Bang theory has 9.9. It is that solid. Okay. So it's solid scientific answers to all these questions. So that's amazing because it seems unanswerable. Okay, but there's an answer to that. Okay, so then the following part is mostly from the textbook, but I try to look for some pictures to make the content more interesting. So to begin, we need to ask, why is the nighttime sky dark? You would say that's nonsense, okay? We all know the nighttime sky is dark. However, if you know that the star count in 2019 said there's a 10 to the 24th in the observable universe, which means all the stars that we can observe, they are that much. And assuming that all the stars project their light on our sky, then in theory, you wouldn't be able to see any dark spaces because there are so many stars. All right? So which is the dark sky paradox by this person. This paradox was proposed in the 19th century, so that was really long time ago. It says, because there are so many stars, our night sky should look like this. Do you ever see a sky like that? I don't think so, okay? So you see a sky, a dark sky, okay? Explanations. The first thing is explanations. The first thing is the universe is finite. Okay? So, and then the background of the universe is dark. And I think the person who proposed this explanation at that time, so this explanation is proposed long time ago. He or she didn't know that there are so many stars. So he thinks if the universe is finite and the background is dark, then in theory you should be able to see the dark background. In theory. That's the first explanation. And the second explanation is the universe is infinite. But there is dark matter, like the clouds here, intercepting the most distant stars. So which means if you are here, then you won't be able to see stars, this one, because it's intercepted by this dark matter here. So these are the two explanations mentioned in the textbook. However, we all know long time ago that there's gravity. So if there's a finite universe and each star has a very large mass, 很大的质量, then at some point they will start to collapse. Actually, this is the origin of the origin of planetary systems or galaxies. They all start from random bumping due to gravity. So if this is finite, then they will ultimately collapse, and ultimately to the center, because they will draw each other closer to each other. So in theory, this should happen. And the second explanation is if these are dark matters here, then you will see the glows, which means if this star is blue colors, then you will see some blue clouds here, like dark nighttime sky with clouds. Then you see the glow from the city. So in theory, this should happen, but this did not happen. All you see is a very clean, dark sky. All right. So, in the early 20th century, this person, he proposed another paradox, which is a cosmic egg. So, he thinks the universe has a shell structure, like an egg, and then it's expanding. However, at that time, he doesn't have any evidence to support his conjecture. It's a little bit like continental drifting, 大陆漂移学说. At the time that this theory was proposed, there was no evidence. So everybody thinks you're crazy. Okay? So it's a little bit like that. It's like mad ideas without any scientific base. Okay. However, I think several years after this cosmic egg proposal, the Big Bang theory came up. So that was really early. Okay, here we will go through the evidence here, but you already know this one. You know a little bit about this one. And this one, I will not talk too much about this because it's a little bit complicated, so we'll focus on this. Velocity and distance. Okay, we start with velocity and spectroscopy. I would like to emphasize again that it's a physical approach to study the chemistry of celestial objects. Celestial means things in the sky. 天体的. So, light is important for the study of chemistry of stars. And let's review this graph. You all know this graph from your high school physics or chemistry. So we have different electromagnetic waves, and light is the electromagnetic phenomena. We have visible light here, a very short range, and the red one has here is wavelength, is longer wavelength. So the red one has longer wavelength. And the blue part here is ultraviolet, shorter wavelength. And shorter wavelength energy here, because it's in reverse relationship, so shorter wavelength, lambda, has higher energy. Just a short review. Okay, then, from your homework, the spectrum of the sun actually has many bands. What are the dark lines? It's from your probably general chemistry course, 普通化学课本. Okay, photon can interact with electron. So when a photon comes in, it interacts with a specific electron, and then it will deliver its energy to this electron, and then it will enter the excited state, 激发态. And then at some point it will return, because the excited state is unstable. Later on, it will return to its ground state, 基本态, ground state, and then it will emit the same energy that it received from the photon. And apparently, this kind of behavior is quite specific. It's a little bit like, I like carrot, 我喜欢吃红萝卜. So when I eat carrot, I will be very excited, but this is not the case for the other person. The other person might be more excited with caffeine. So this is specific for the element, for the different atoms. Therefore, you all know there's no student from 简波通时代. So you all know these techniques, atomic absorption, which actually makes use of this behavior of atoms to quantify the amount of specific element in your sample. This behavior. And then, here comes the homework one. We have different light. This is a long wavelength. This is short wavelength. And this is the reference spectra from hydrogen and from sodium. And these are from laboratory. Alright? And this is the sun's spectrum with many more dark lines. Okay, so here, Sally actually, I think you use some text in the textbook. So it's a little bit like a knowledge without a further understanding or deep root. Okay, so here we will know a little bit more about the stars for the following few weeks. But here it actually says, usually if an object like a star is hot, then it should emit continuous spectrum of radiation. It should be continuous. Alright, so it has every wavelength. However, for a star, it's hotter in the middle and cooler at the outside.
And therefore, those elements at the atmosphere of a star. You are wondering, I think the star is like our sun is made of gases. Is there a difference between atmosphere and non-atmosphere? Here, actually, it means the outer part of the star. Actually, every star has its own structure. We will talk more about this next week. And here is saying that it's actually the outer atmosphere that is cooler. And then, therefore, the atom there, their elements might be at the ground state. And then, therefore, the element, the electron can absorb photons from the inner part of the star. And then, this will create these dark bands. And it corresponds to the transition between different energy levels, which means ground state or excited state. And this leads to the dark lines. All right, here it says redshift, and Sally already explained this. Okay, the lines are shifting toward the red. Okay, I skip this. You know this well. All right, here just another more saying. It's also written in the textbook that the redshift can help you to quantify the speed, which actually corresponds to the question or the answer for the group B question. How do they know the speed, the number, or the value of the speed? This is because it's you can use it to quantify, all right? So, for example, if this is now moving and the speed of sound is this one, then in theory, this is a theoretical, so somebody will hear 100 beats per minute. But if it's moving towards you at a speed that is 10% of the sound speed, then you, as an observer, you will hear 100 plus 10 beats per minute, 10% more. And the other way around, for objects that's moving around away from you. That's the reason you can measure the speed, because we know the speed of light. So they can use the speed of light and the redshift to estimate the speed of the objects. Okay, summary. If the object is approaching the observer, the frequency will be higher. Okay, you answer the question, so I will leave it here. Here, before the talk, before the break, I will shortly talk about the distance because this is much more difficult. Okay, we will start with the easiest part, which is geometry. And as Hank answered, said in the Q&A session, the basic approach was triangulation, 三角测量法. And it's quite easy. I remember when I was a freshman, 大一学生, one of the assignments was that you have to draw the map of the 醉月湖 in 台大. You might think, oh, that's a easy peasy. You just Google map the 醉月湖, and then you just make a copy of that. But you need to know that by that time, there's no Google. Alright? So, and then what we were asked to do is you walk to the 醉月湖, and then we just measure, okay, here, you know, there's a curvature of the lake. Then you measure, okay, from this point, there's an angle of that, and angle of that, and how many distance you need to walk, and so on. And therefore, you draw the curvature or the contour of the lake by hand. Okay, it's a little bit like triangulation. So here, we talk about triangulation. You should have at least 2 points, and then you measure the angle to your objects. Then you should be able to determine this distance from the rock to the baseline. That sounds easy, but when you consider that you need to do that in the space, it's not that easy. Okay, here this is not in the textbook, but I just shortly explain you. So Hank said a term called parallax. I think the Chinese is 视差. I think so. Okay, so this is the triangulation in the space. The idea is very simple. Consider this. There's a star here, and then, as I said, you need 2 points. And you need a straight line, right? So the easiest way is to use the orbit of the Earth around the Sun. So for example, you measure the objects, you measure the angle here when it's summer, and then when the Earth comes here, you measure again in winter. Then you will have the distance and the angle. Then you know the distance. This is called annual. Now you don't know why. Because you measure again in summer and measure again in winter. So you measure annually. 年视差. Okay. So, and here there's some basic units for you. In astronomy, AU means astronomical unit. 1 AU is the distance between the Earth and the Sun. So the annual parallax has a baseline of 2 AU. And you can imagine that the limitation is you need to be super precise. How precise do you have to be? Okay, here's a number for you to consider. So this is the baseline, 2 AU. And then this is the star. Now we want to measure. You can only measure star because star gives you light. You cannot measure planet. 你只能测量恒星，你不能测量行星。行星没有光 okay? So you can only measure star. And star, the distance, the nearest distance is 10 times 10 to the 17th. That's a super long distance. Okay. And so you need to, how precise do you need to be to measure the distance? It's like this. Arc second, which means 1 arc second is 1 to the 360 degree. So you need to be that precise. And if your error happened to be 1 arc second, that means a distance of 3.26 light years. 就是你有360度的这个误差，你的距离差别就是误差就是3.26光年。So you can imagine how large the error is. Okay, it's incredible. And apparently, if the object is so far away, you cannot use it. So this can only be used for objects close to our planetary system, to the solar system. Then there's another kind of parallax called secular parallax. This term, secular, you probably see that from time to time in papers. 永世的, okay, it's a strange term. But here, what it's saying is, astronomers figure out that we are in the Milky Way, 银河系, and they are, as I said, all the celestial objects, they are mostly rotating, including the Milky Way. There are several arms. And they figure out, I don't know how, they figure out that the period of the cycle. That's amazing. Okay, 他们知道这个旋转的周期. Okay, therefore, what you can do is, if you now want to measure, use this secular parallax, you measure the angle of that star to that star this year. And then you measure maybe 50 years later. Alright? Then you should be able to know the distance. So you know the astronomy is the work of many generations of scientists. That's the reason why. So you use this kind of secular parallax, you will be able to determine most of the distance to the stars within the Milky Way. Then you think, wow, just for the Milky Way, we know there are so many other galaxies. What happened to them? Okay, that will be the topic for the next week, next hour, 1 hour.